Let's move on to Lesson 8.2 in Geometry. We'll be learning about tangents. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point, which we call the point of tangency. A tangent segment is a segment of a tangent line that contains the point of tangency. Let's take a look at the drawing. So we have circle O, and we have two lines that are interacting with circle O. From our last lesson, we should recognize that line MH is a secant, and that line passes through MH at points MN, creating a chord. What we're interested in this lesson is line DH, which is this line right here. And DH intersects the circle at point F. We call this the point of tangency. We have a tangent segment, and that tangent segment that also intersects the circle is segment DG. So you have not only the whole line DH, but you have segment DG. You could also call the segment DF if you want to. You could actually name the line DF. The important thing that will be going on is that you use the symbols correctly to go along with your definitions. So tangent line will have the double-sided arrow over it. Tangent segment will you have your straight line over it. Point of tangency is simply named by the letter of the point. So for our first theorem, Theorem 8.2.1, let's look at our drawing. We have a circle. We have a line AB, which is drawn tangent to that circle. And we're going to find out right now what tangent means. If a line AB is tangent to a circle O, then it is perpendicular to a radius, which is OA. So let's look at OA, and we'll look here at line AB. And what happens here is that we have a perpendicular line interacting with that radii. It creates a 90-degree angle. We have the converse of Theorem 8.2.1. Notice same drawing. It tells you if line AB happens to be perpendicular to radius OA at the point on the circle O, then the line is tangent to circle O. So if we go back and forth and look at both of these, 8.2.1 says if a line is tangent. 8.2.2 says if a line is perpendicular. So be sure that you have the differences in your notes. Let's look at example 1. We have a circle. We have a circle. We have two lines drawn outside of the circle. They appear to intersect with the circle, and we'll see. So it says find the measure of each angle in quadrilateral ABCD. So this is a four-sided figure. You can see that two auxiliary lines or axillary lines have been drawn, and so we can call it a quadrilateral. So find the measure if AB, that's this segment going from point A to point B, and AD are tangent segments. Okay, so they tell us that they are tangent, which means that we have 90-degree angles at the point of tangency. And let me, it looks a little bit more like a square there. The measure of angle B and the measure of angle D equal 90 degrees. So this is our first step after what information we were given. Now we have the quadrilateral, and what we can do to solve for the measure of each angle is to remember all our properties about quadrilaterals. First of all the angles in a quad equal 360 degrees. So using algebra, you will add each individual angle. So we have x, let's start with A, we have x plus B, which we know is 90, plus C, which is 3x, plus D, which is 90, equals 360. Adding like items, we have x plus 3x, which is 4x, 90 plus 90 is 180. Subtracting 180 from both sides, we have 4x equals 180, dividing 180 by 4, and x equals 45. So, we already knew what the angles B and D measure. Now, solving for x, we know that the measure of angle A also equals the measure of x, which is 45 degrees, and angle C is 3 times x. 3 times 45 is 135. Next theorem, tangent segments AX and BP from an exterior point X to a circle are congruent. Now this is very important to the things that you're going to be doing from now on. If we draw these lines using the line postulate, we have two radii, AP and BP, that we drew. We can also draw a line XP from this outside point to the center of circle P. Note that they form two triangles. We know one thing about these triangles is that AP and BP are congruent. We also know that XP is congruent for both of them. So guess what? By using congruent triangles and using side and side here, we know that the third side of two congruent triangles is congruent if the other two sides are congruent. So AX and BP are congruent. Anytime you draw these shapes from two perpendicular points, two tangent points, you will have congruent lines. When a circle is inscribed in a polygon, each side of the polygon is tangent to the circle. These are some facts that grow out of the last theorem we were looking at. If you see this inscribed circle in the triangle, it actually looks like those lines that we drew. So in these figures, these sides would be congruent to each other. Okay? The same goes if you have other polygons. You could now say all the way around this square that these sides were congruent. In fact, because this is a square, if you had actually been told it was a square, all of the sides would be congruent. And in the triangle, if you knew that was an equilateral triangle, you could say that all of those sides would be congruent also. So when a circle is inscribed inside a polygon, each side of the polygon is tangent to the circle. The polygon is said to be circumscribed about the circle. So we've had circles circumscribed about polygons. This is the polygon circumscribed about the circle. Let's look at example 2, and here we have a quadrilateral, and it has a circle inscribed inside. So that means that you will be set with congruent segments. Now, this quad obviously is not a regular quad, so what will be happening is it will have different congruent marks. So, what do we know? We know that PW equals PZ. And we know that QW equals QX, that RX equals RY, and SY equals SZ. Because we know that, we can find the perimeter of the quad. And we do that by adding all the sides. Now realize, because each one of these sets is a set of congruent sides, you can use multiplication instead of adding 8 sides together. You can use multiplication for each length. So you can see here that it's set up 2 times one side, 2 times the next set of sides, and so forth. And when added together, that becomes 22.8 centimeters. We have another definition. A common tangent. Now, tangents is what this lesson is about, but tangents have different properties, and this is one of them. A tangent common is a line that is tangent to each of 2 coplanar circles. That means they're on the same plane. So, you have tangent C. Tangent C, you can see, interacts with both circle B and circle A. So it's common to circle B and circle A. Tangent D is also common to circle B and circle A. Now in this situation, you see that the 2 tangent lines, C and D, intersect on the inside of these 2 circles. So they're called common internal tangents for inside. Now if we look at the drawing to the right, we have the same circles, A and B. We have 2 tangent lines, F and G. But these lines, though they intersect with both circles A and B, do not intersect with each other. So the lines do not intersect with each other. They are on the, let's say, outside of the circles. So they are called common external tangents. And the first set were common internal tangents. Besides having tangent lines, you can also have tangent circles. And this gets a little confusing. So besides having lines that are tangent to a circle, you can have tangents common to 2 circles internally and externally, like we showed in the last slide. But you can also have tangent circles common to the same line internally and externally. You'll be expected to identify drawings of each one of these situations, so you should have drawings in your notes with quick explanations next to them, and you should study these different situations. So tangent circles are coplanar circles that are tangent to the same line at the same point. So here's our tangent line, and we can see that all 3 of these circles, MN and P, are all tangent to that same line. N and M, if you can note, are on one side of the line. They're both on, and I'm just going to say this, it doesn't truthfully apply, but on the left side of the line. And they are called internally tangent circles. So they're they're considering this to be inside of the line. Now, you notice that P is on the other side. So, P and M are externally tangent to each other because they are on opposite sides of their common internal tangent line. So, I suggest you make a drawing where you have P on one side and M on the other side, and then have the definition of externally tangent circles, because they are on the opposite sides of their common internal tangent line. So let's try that one more time. This tangent line is now known as the common internal tangent line to M, circle M and P, which are externally tangent circles. N and M are internally tangent because they're on the same side of their common external tangent line. So that tangent line changes names according to the situation of the circles that are drawn. So be sure to draw both different sets of circles in your notes. Lesson 8.2 should be fairly straightforward. Most of the questions are definitions and or drawings. The drawings will take you a little while, so give yourself a little bit of time. And just some hints. Number 4 is asking you what type of quadrilateral is it. Number 10 is similar to example 2. And number 29, draw a picture before trying to solve. You should do that with all of your work, but in this one particularly, you'll need to draw a picture. They do not provide one. If you have any difficulty, be sure to contact me, and I'll talk with you again in lesson 8.3.